Alright, welcome to Calculus. So this video is attached to a project that I have my students do in my Calculus 2 class. And the idea is that I actually have them find the volume of a donut and some other object. And I'm going to look at all those objects and how we can cut those objects up into different shapes and what we need to do in order to build the equations so that we can find the objects for the said items. Now to start with, this is actually a 3D printed donut. I guess a tubular dough ring, or I know there's a fancy name for it, but we're just going to call it a donut for now. This is one a student printed off for me a few years ago, and I've just kept it because it's been a really good tool for that. So the things that we need to talk about when we start rotating this is thinking about how we're going to cut the donut. So if we slice the donut across this way, what we end up with on paper is having a circle that we can then rotate around the y-axis, and when we rotate that circle around the y-axis, we end up with this shape, if you will, coming up out of the paper like that. Okay, so that gives us an idea of what measurements we need. First and foremost, we need to know the center of that, which we can place just about anywhere we want to. Well, kind of, we can place it on the x-axis, but what we need is the distance from here to here. So we'll call that, say, we'll call that value from here to here, we'll call that R1, all right? Just because it's a radius of a circle. And then we have this circle right here that the donut's actually, if you break the donut in half and you have the cross section there, that piece right there, then we have this radius, which we'll call radius 2 for right now. These are all, you have to kind of decipher which ones are useful and which ones aren't useful to us as we go through this. And that really, for the most part, takes care of most of our measurement of what we need. Now, how do we end up doing those measurements? Now, from there, keep in mind that based on these measurements, we're going to need to do other things with it as well, right? So to kind of think about this, if you have calipers, this is a lot easier, by the way, but I couldn't find my set, so who knows where they are. So I'd set this up, and I would actually measure to where the center of the donut is. In this case, it looks like it's right about here, so whatever that measurement is, and this might actually be a lot easier using the metric system, and be a little bit more accurate at least. Looks like it's about 4.5, maybe 4.7-ish centimeters to the center there. So that R1 value for mine would be about 4.7 centimeters, and keep track of your units. And then, of course, you need to figure out the actual measurement of the dough, the ring itself, which it looks to be about 3.7 maybe. So that diameter of this thing is 3.7-ish centimeters, which means that the radius would be half that, or 1.85 centimeters approximately. And again, calipers would be very useful in this situation. And there are other ways you can figure those out, but those are the pieces you need. And then from there, you can build the equation for this circle, right? And then you know what this distance right here is, which tells you that point. We know the y-coordinate there, the way I've set this up, is 0, but the x-coordinate we don't know, and that's just simply going to be whatever this R1 value is. And so in my case, this is 4.7. 0 is that center, and that gives us the center of the circle. We know the radius of the circle, and then once we have all that, and we're rotating it around the x-axis, then it's just a matter of setting up the equations. Now, it gets a little tricky. You do have to kind of think about this in terms of pieces, because if you just try to integrate the entire thing at one time, you run into problems because it's not a function. So you do have to kind of force it to be a function. And in fact, it's easiest to make it two separate functions right there, and then keep in mind that it is symmetrical from top to bottom, and that's going to help quite a bit as you start to work this problem out. And then you use shells or washers to find that volume. But that's just thinking about, the idea here is to think about how can we split these objects up into finding out their volume. How can we subdivide them? So let's look at another example. This is another 3D object that has been printed off. And I don't remember if I printed this one or someone else printed it for me, but let's go with someone else printed it for me. And it's just a black box, if you will. All right, so it's a rectangular prism. So how do we find that? Well, that's not a rotation like the dough ring was a rotation, but this one's not a rotation. So how do we do this? Well, we still want to think about placing this on top of the x-axis somehow, right? So maybe it's easiest just to kind of set it right there. I don't know, you can't see that terribly well in the viewing window we got there. But there we go, right? So the idea being is that we want to figure out this dimension going across and this dimension going up and down. What are those? So I'll get out my handy dandy ruler. Again, I find that's 3.7 across. So if I'm going this way, this would be 3.7. And going up and down, it is exactly 5 centimeters. Well, I know that wasn't me because I would have made that exactly 4, but oh well. So we have that line and that line right there. So we have x equals 3.7 is one line, and we have y is equal to 5 as the other line. And then we just need to figure out, well, this is our area right here. This area is always length times width, right? That's how we always do this. And anytime you're using the shells methods or the washer method, what you're doing is you're finding area, you're integrating area to find the volume. So in this instance right here, when we integrate this, we still need to integrate the area according to a particular variable here, again, right? However we're doing that. In this case, we might be thinking about it coming up out of the paper here, so maybe we're dealing with the z-axis instead of x or y. But we still need to do that, and that area in this instance would just be, well, this is a constant rectangle here, so it's just 3.7 times 5, and we'll go ahead and say dz. Well, how do we measure dz? Well, in this instance, we'd be measuring from there to there, which works out to be 8.8. So we'd be measuring from 0 to 8.8, and that allows us to find our volume. And this is when this object right here is, this cross section here is constant. Okay, so it's a constant shape, it's not changing any, and there's no variables involved, so it's pretty solidly consistent for us. Now what else can we do though? So let's do a rectangular prism and we can figure that out. Keep in mind that this would be a pretty basic shape for a pool as well, right? So think about what are the types of shapes we can do this with? Well, a triangular prism would be that cross section. Instead of it being a rectangle, if we were to build that out, there it is right there, right? Not exactly drawn to scale, but pretty close, right? So there's our shape. This is, of course, an equilateral, and I didn't draw one of those, but you get the idea is that we just need to make those measurements so we can define the outside edges on the paper somehow. However you want to do that, whether you want to make one of them the x-axis, so then maybe really what we do there is we set this up so that we have our two equations down there, right? And then we'd figure out what y1 is, and we'd figure out y2 is, and we'd build those equations from there, right? And that'll be all based upon our measurements. But again, this would be a constant area for this one. Well, what if it's something like a pyramid, something like this, where they're not the same all the time? But and even here, they're still talking about similar shapes, because in this instance, how would we build this? Well, coming up out of the paper doesn't make a whole lot of sense. So if we were oriented this way, if we set it up so that it is oriented across the x-axis like that, well, that makes us think about how we're going to build this up. Well, it means that we're dealing with a line coming this way and a line coming that way, and then we have these cross sections, and each cross section is, if I pull that cross section out like a loaf of bread, if you will, each cross section is a square. You think about the base of this rectangular pyramid here, or square pyramid, like those cross sections are all going to be square, right? So that's S and S, so the area here would be S squared. So if I can identify that distance from that side right there, which is just the distance between the two equations, we'll call this F and we'll call this one G. In that case, S would just be F minus G in this instance. I know we're adding them together, but the fact that G is going to be a negative quantity because it's below the axis there, we're going to need to subtract them. If they were both above the axis, we would still need to subtract them. So either way, we end up with that. So then we're just need to figure out these measurements, these equations that describe this outside edge of our pyramid there, and we can build that up. So the idea here is that when we have similar shapes, we still can deal with doing the integration. In this case, it would be integration of s squared. And in this case, the way I was doing this, those would be dx's going along that way, and then you'd have a would be equal to some x1 value, and b would be equal to some other x value, right? And you just build it up from there. In this case, it's just s squared. There's no, if you're talking about the washer method, you would put a pi in there, because what we're integrating is a circle. We're integrating the area of a circle from a to b to find the volume. Here we're integrating a square from a to b to find the volume. So it's just s squared. So anytime you need volume, the basic idea is the integration of an area from a to b. Okay, so think about that as you look at objects and think about, how can I subdivide it? How can I slice that in such a way that I can find the individual pieces and then add those individual pieces together to define the volume? All right, I hope this was helpful and useful. Reach out with questions and comments as you have them.